Good morning, everyone. Today we will study the effect of rise of temperature on the cables. In the previous lecture, we studied about the analysis of the cables when the supports were at different levels. Now we will see that what kind of effect is produced in the cable, that what effect is produced in the horizontal thrust and the depth of the cable whenever there is an increase in the temperature. Suppose small l is the span of the cable. By span of the cable, I mean to say the horizontal distance between the supports. Let small h is the depth of the cable. Depth is the maximum depth of the cable. Now we know that the length of the cable subjected to a UDL is equal to small l plus 8h square by 3l. Now if you see this equation, see small l, which is the horizontal distance between the supports of the cable, is a constant term because that distance is not going to change. Now if I differentiate this equation, see the differentiation of capital L will become dl. Small l is a constant, therefore the differentiation will be 0. 8 by 3l is a constant, and h square differentiation will be 2h into dh. So after differentiation, I will get dl equal to 16h by 3l into dh. After rearranging this equation, I will get the equation of small dh, that is the change in the depth due to the increase in temperature, equal to this, where small dl is a change in the length of the cable. So let us take this equation as equation number 1. Now let the rise of the temperature is T degrees Celsius. We also know that whenever there is a rise in temperature, the increase in length is also equal to alpha TL, where alpha is the coefficient of thermal expansion, T is the rise in temperature, and capital L is the original length of the cable. After putting the value of capital L, here I will get this equation. After simplifying, after opening the bracket, I will get the increase in length as alpha TL plus alpha T 8h square by 3l. Now if you see this equation, and we can ignore this term because this term is very small, and therefore dl can be written approximately equal to alpha T small l. Now let's take this equation as equation number 2. Now after putting the the value of dl from equation number 2 in equation number 1, I will get the value of small dh equal to 3l by 16h into alpha TL. After rearranging this term and simplifying this equation, we will get dh equal to 3 by 16 alpha TL square by h. So this is the equation of the increase in depth. So suppose if we want to find out that what is the increase in the depth due to increase in the temperature, the increase in the depth can be found out by this equation. We will be knowing the value of coefficient of thermal expansion for the cable. We will be knowing the value of increase in temperature. We will be knowing the horizontal span between the supports of the cable, and we will be knowing the original depth of the cable. So after putting all the values, I can get the value of increase in depth. If you see this equation is coming in positive. See, the positive value indicates that whenever there is an increase in the temperature, the depth will increase. The positive value means increase in the value. So the increase in depth can be found out by this equation. Now let's come to the analysis part of this cable. See, suppose this is your cable. These are the suspenders of the suspension bridge, and suppose this is the deck on which the traffic will move. Suppose the load on this deck is W per unit length, that is UDL is acting on the cable. See, if we say that, see, if you see this diagram, this UDL is acting on the deck, but we say that this UDL is acting on the cable because whatever the load acts on the deck, it ultimately gets transferred through the suspenders to the suspension cable. Therefore, we can say that the cable is subjected to the UDL. Now, in this diagram, suppose C is your lowermost point and the depth, that is the depth of the cable, is small h. Suppose small l is the horizontal distance between the two supports. Now as we have done till now, At supports A and B, there will be two reactions. One will be a vertical reaction VA and VB, and other will be a horizontal thrust acting in the outward direction. Now, if I take the moment about C point equal to 0, see, we know that the moment at any point in a cable is 0. So therefore, I can take the moment at any point equal to 0. So I'm taking the moment about C point equal to 0. See, whenever I take the moment about C point equal to 0, either I can take the left part of the point or I can take the right part of the point. So in this equation, I have used the left part of the C point. See, if you see the left part of the C point, there are three forces. One is your VA, which is acting in the upward direction. The second is your horizontal thrust, and the third one is your UDL. So VA is acting. See, we are going to take clockwise value as positive, anti-clockwise as negative. If you see VA is acting in the upward direction. So VA will produce a clockwise bending moment about C. So for clockwise, it's positive, and the perpendicular distance of VA from C is L by 2. So therefore plus VA into L by 2. If I see the second force, that is capital H, capital H will take C point in the anti-clockwise direction. Therefore, it will produce an anti-clockwise bending moment. So for anti-clockwise, I'm going to take minus, so minus, and the perpendicular distance of the line of action of capital H from the C point is small h. So minus h into h. Third force is this UDL. So this UDL is acting in the downward direction. So this UDL will take the C point in the anti-clockwise direction, or it will produce an anti-clockwise moment about C. So for anti-clockwise, I will take minus. Now convert this UDL into point load. So see, we are looking at the left portion of the C point. Okay. So UDL can be converted into a point load by multiplying it with the length of the UDL. So on the left of the C point, the length of the UDL is L by 2. So minus W into L by 2. So this is your point load, and this point load will act at the center of L by 2, that is L by 4. Half of L by 2 is L by 4. So therefore, the perpendicular distance is L by 4. This equal to 0. From this equation, after solving this equation, I will get capital H into small h equal to VA into L by 2 minus WL square by A. See, now if I have a straight beam, if I suppose if I have a straight beam, and these were the two supports, and in this straight beam, if I apply the same load which is acting on this cable, so see, on the left part of C, there will be two forces if I ignore capital H, and after ignoring capital H, there will be two forces. One will be VA and the second one will be a UDL. So if I apply VA and UDL on the same straight beam, I will get the equation of MC equal to this. So I can write this equation as MC. I can write this term as equal to MC, where MC is the beam moment. Beam moment means if I apply the same loading in a straight beam, the bending moment in that beam is the beam moment. So this term can be replaced by MC, which is the beam moment at C. So from this equation, I can find out the value of capital H equal to MC upon small h. And after differentiating both sides with respect to small h, I will get, see, dh d capital H by small dh equal to MC is a constant, so therefore it will remain the same, and the differentiation of 1 by h will be minus 1 by h square. After rearranging this term, I will get this equation, and again rearranging this term, I will get small dh upon capital H equal to minus 1 by h into dh. Now we already know the value of small dh. So if I will put the value of small dh in this equation, I will get the final equation small d capital H upon capital H equal to minus 3 by 16 L square by h square into alpha t. See, so if I see this equation, and this equation is coming out to be in negative. It means whenever there is an increase in temperature, the horizontal thrust decreases, and the decrease in the horizontal thrust can be found out by this equation after putting all the values.